Good morning, and the following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to wrap up the last chapter. We're going to take a brief look at something from 11.6, then go on to 11.7. Your homework, you're going to have 11.6, 11.7, and the chapter review. Tomorrow we'll review for the test on Friday. Okay, so let's get going with section 11.6. And first of all, I want to go back and look at a problem I introduced at the beginning of this chapter, or near it anyway. I said 2 cubed equals 8, and 2 to the 4th power equals 16. But what if 2 to the x equals, and I can't remember what number I chose between 8 and 16. Let's just go with 11, okay? So then I said, how are we going to solve 2x equals 11? And then we introduced the idea of a logarithm, and we could say log base 2 of 11 equals x. Or I'm going to write that this way and say x equals log base 2 of 11. The problem with that is most of our scientific calculators don't have log base 2 on them. So how do we calculate that using a calculator? There's something called the change of base formula, and this is what it says. It says log base b of x equals log base a of x over log base a of b. So we're taking log base b of x and splitting it up, taking log base a of the top, the x part, and log base a of b, what was it before the base? Keep in mind for a, we're going to want to use either log base 10 or base e. So for instance, this problem could be written as log base 10 of 11 over log base 10 of 2. Now, I don't need to write the tens there, but I just wanted to emphasize I could write it that way. Or I could write it as the natural log of 11 over the natural log of 2. I'll get the same answer either way, but you don't want to have one of them base 10 and one of them base e. Both the log on top and bottom have to be the same. So let's see here on our calculator. If we do log base 10 of 11, close it up, divided by log base 10 of 2, I get 3.45943, etc., etc. If I take the natural log of 11 divided by the natural log of 2, I get the same thing, okay? So there you have the change of base formula. Let's look at some examples of that. And so, or some more examples, I should say. Let's say we've got log base 3 of 7. We could rewrite that as log base 10 of 7 over log base 10 of 3. And going to the calculator, we have log base 10 of 7 divided by log base 10 of 3. And what do I get? It says to go to 4 decimal places, 1.77124, etc. The 4 would round down, so 1.7712. How about log base 7 of 3? Well, this time let's use natural log. So we'd have the natural log of 3 over the natural log of 7. And the natural log of 3 divided by the natural log of 7. We get 0.56457, etc. Rounding at the 5, the 7 would round up 5646. Okay. So that's how you use the change of base formula. Now we're going to go on to chapter 11.7. Okay. And in 11.7, we're going to talk about half-life, radioactive decay. Let's say that there's 64 Snickers bars in a refrigerator. and I come back 1 week later, and half of them are gone. There's 32 of them now. And I come back 1 week later, and half of those are gone. There's 16 now. And I come back 1 week later, and half of those gone, and then half of those, 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 and then half of those. It just keeps halving. So every week that goes by, half of them disappear, or we'll say die off. So what we have here is a half-life situation where the length of time of the half-life is 1 week. Now, 2 half-lives do not a whole life make, or no life at all. In other words, you don't lose 32 the first week and 32 the second week. You always lose half of what was there at the beginning of the time period. That's the half-life, okay? All right, now, the formula for that looks like this. A equals a sub 0, 2 to the negative 2, excuse me, the negative t over h power. All right. Now, even though 2 is positive in this formula, because the exponent is a negative 2, that's the same thing as having 1/2 to the positive t power. So basically, this still works as a half-life formula. All right, we're going to come back to that formula in a bit. Just wanted to get it out there while I'm thinking of it. Let's take a look at this problem. 6 to the x minus 2 power equals 36. We're supposed to solve this equation for x. If we could write it so that the base was the same on both sides of the equation, then the exponents would be equal. Because exponentials and logs are one-to-one functions, we can do this. So what I could do, I could rewrite 36 as 6 squared. So now on both sides of the equation, I have 6 raised to a power. Therefore, the exponents are equal. So x minus 2 equals 2. Add 2 to both sides, x equals 4. Let's check our answer. 6 to the 4 minus 2 power is 36. 6 squared is 36. 36 equals 36, and it checks. All right. Let's take a look at another example. 5 to the 4x power equals 1 over 125. Well, 125 is 5 cubed. So what I could do, I could take 1 over 5 cubed and write it as 5 to the negative 3 power. Usually we don't take a positive exponent and rewrite the term so that it has a negative exponent, but here we wanted the bases to match. So now that I've got 5 on both sides, 4x equals negative 3, divide by 4, x equals negative 3/4. And let's see here. How about this one? 4 to the x power equals 5. Well, now I've got a problem because I don't know how to take 5 and write it as 4 to some power. But what I can do is this. I can change this exponential equation into a logarithmic equation. And what would it look like? It would be log base 4 of 5 equals x. But using the change of base formula, I could write that as log base 10 of 5 over log base 10 of 4 and punch that into my calculator. So let's see here. Log base 10 of 5 divided by log base 10 of 4. I get 1.160964047. These instructions said to approximate to 4 decimal places, the 6 would round up, so 1.1610 would be our answer to 4 decimal places. Okay. How about this one? 13 to the x minus 2 power. Sorry. 13 to the x minus 1 power equals 2. So I can't take 2 and write it as a power of 13, at least not off the top of my head. So I'm going to change this to a logarithmic equation. Log base 13 of 2 equals x minus 1. I'm going to add 1 to both sides. So I've got 1 plus log base 13 of 2 equals x. Or I could say x equals 1 plus log base 13 of 2. Using the change of base, I could write this as 1 plus log base 10 of 2 over log base 10 of 13. And then go to the calculator. 1 plus log base 10 of 2, close it up, divided by log base 10 of 13, close it up, and I get 1.270238, etc., rounding to 4 places. The 3 rounds down, so x equals 1.2702. Let's see here. Let's take a look at one using base e. So e to the 2.9x power equals 4.5. I have no idea how to take 4.5 and write it as e to some power. So if I can't match the bases, I'm going to play baseball, change this into a logarithmic equation. So log base e of 4.5 equals 2.9x. But log base e is natural log. So natural log of 4.5 equals 2.9x. I'm going to divide both sides by 2.9. So x equals the natural log of 4.5 over 2.9. Calculator time, natural log of 4.5, close it up, divided by 2.9. 0.518647. The 4 would round down, so 0.5186. Okay, let's see here. Now let's say we have this equation. Log of 2x equals 4. Keep in mind, there's an implied base 10 there. So now I can take this logarithmic equation and change it into an exponential equation. It would become 10 to the 4th power equals 2x. Divide both sides by 2. 10 to the 4th power divided by 2 equals x. Well, 10 to the 4th power is 10,000. So x would be 5,000. Let's see here. How about this one? Log base 4 of 2x minus 1 equals 3. So we get 4 cubed equals 2x minus 1. 4 cubed is 64. 64 equals 2x minus 1. Add 1 to both sides. 65 equals 2x. Divide by 2. X equals 65 over 2, or what, 32.5. And let's see here. Now, what if we've got this situation? Log of 3 minus 2x equals log of x plus 24. Again, just like if we have a base to a power equals the same base to another power, if we have log with a base of something with log of the same base as something else, we can take the quantities that the logs are being taken of. In other words, we can write this as 3 minus 2x equals x plus 24. I don't really need those parentheses there. Okay. Log base 10 of that equals log base 10 of that, so that equals that. I'm going to subtract x from both sides. 3 minus 3x equals 24. Subtract 3 from both sides. Negative 3x equals 21. Divide by negative 3x equals negative 7. Okay. Let's see here. Let's do one more of those. Let's see, we have the natural log of 3x plus 1 equals the natural log of x plus 7. So then 3x plus 1 equals x plus 7, because we're taking log base c of both sides. Subtract x. 2x plus 1 equals 7. Subtract 1. 2x equals 6. Divide by 2. X equals 3. Okay, now let's take a look at some problems where we're going to use that formula that I introduced a little while ago. A equals a sub 0 times 2 to the negative t over h power. A sub 0 is the starting amount, a is the ending amount, t is time in whatever units are used, and h is the half-life in the problem. All right, it says tritium or tritium, I'm not sure how you pronounce it, but it says the half-life of tritium is 12.4 years. So the half-life is 12.4 years. How long will it take? So time is the unknown. For 25% of a sample of tritium to decompose. They don't tell us the starting amount. So the starting amount is just a sub 0. They don't tell us the ending amount, but they do say this. How long will it take for 25% to decompose? So at the end, we've lost 25% of a sub 0. So at the end, we still have 75% of a sub 0. So the ending amount is 75% of the starting amount. All right. Now, again, we don't know the beginning amount or the ending amount, but as you'll see, we don't need to, as long as we know the relationship between them. So plugging these quantities into the formula, for A, we're going to put 0.75 a sub 0 on the left side. On the right side, we'll have a sub 0 times 2 to the negative t over 12.4 years. All right. Let's see here. Now, I'm going to divide both sides by a sub 0. So I get 0.75 equals 2 to the negative t over 12.4 power. I can now change this into a logarithmic equation. Log base 2 of 0.75 equals negative t over 12.4. I'm going to multiply both sides of the equation by negative 12.4. On the left, I get negative 12.4 log base 2 of 0.75. On the right, the 12.4's cross out, and the negative times negative makes positive. So now I've got t. I'm going to rewrite this with t on the left because I still need to use the change of base formula on this piece. So I'm going to write log base 10 of 0.75 divided by log base 10 of 2. And that's what I'm going to punch into the calculator. Negative 12.4 log of 0.75, close it up, divided by log of 2. I'm getting 5.146464991. And let's see what they said. They didn't tell us, but they rounded to the nearest 10th of a year, probably because the half-life was given to the nearest 10th of a year. So this would be 5.1 years. Okay. Let's take a look at another example. Let's see here. This says radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. All right, so we're going to use A equals a sub 0 times 2 to the negative t over h time. Time is 2 years. It says in 2 years, 20% of a radioactive element decays. Find its half-life. All right, so the half-life is the unknown. We still don't know the starting amount or the ending amount, but it says that in 2 years, 20% decays. So the starting amount is a sub 0. The ending amount, if we lose 20%, would be 80% of the starting amount. 80%, 0.80, or just 0.8. So now our equation becomes 0.8 a sub 0 equals a sub 0 times 2 to the negative 2 over h power. We're going to divide both sides by a sub 0. 0.8 equals 2 to the negative 2 over h power. We're going to change this to a logarithmic equation. Log base 2 of 0.8 equals negative 2 over h. Well, now we've got a problem. The last one, the thing we were looking for was up on top, and it worked out nicely, but we want h, and h is on the bottom. So what we're going to have to do, we're going to multiply both sides by h, which is going to give us h log base 2 of 0.8 equals negative 2. Then we're going to have to divide both sides by log base 2 of 0.8. So now what have I got? I've got h equals negative 2 divided by the log of base 2 of 0.8. Okay, so I'm just recopying that on the next page. Going to have to use the change of base. So h equals negative 2 divided by the log of 0.8 over the log of 2. And I'm going to group that whole thing together. So in my calculator, I'm going to put in negative 2 divided by parentheses log of 0.8, close up that parentheses, divided by log of 2, close up that parentheses, close up the whole thing, and I get 6.21. And they say about 6.2 years. Now, again, I want to tell you what I put into the calculator. I put negative 2 divided by parentheses log 0.8, close parentheses, divided by log 2. So I had parentheses around this, but also around the whole denominator. Okay, so be careful of that. Let's see here. Here's another radioactive or half-life problem. It says carbon-14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. How old is it? So let's change over. A equals a sub 0, 2 to the negative t over h power. It says the half-life of this is 5,700 years. Okay. Time is what we're looking for, the unknown. So again, our starting amount and our ending amount. It doesn't tell us. It says a bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. So the initial amount is a sub 0. Now, in the previous two problems, they told us what decayed, so we subtracted that from 100%. But in this problem, they tell us what is left. And it says it has 60% of what began. So the ending amount, A, is 60% of a sub 0, or 0.6. Okay, so now our equation becomes 0.6 a sub 0 equals a sub 0 times 2 to the negative t over 5,700 years. I'm going to divide both sides by a sub 0. 0.6 equals 2 to the negative t over 5,700 years. I'm going to change this to a logarithmic equation. Log base 2 of 0.6 equals negative t over 5,700. I'm going to multiply both sides by negative 5,700. We did something similar to this a little bit ago. What that gives me is negative 5,700 log base 2 of 0.6 equals the 5,700s, the negative and the negative. So we get that. Using the change of base, that's negative 5,700 log of 0.6 over log of 2. And putting that into the calculator, negative 5,700 log of 0.6, close it up, divided by log of 2, close it up. And I get 4200.703887. And because the half-life was given to the nearest 100 years, they wrote their answer to the nearest 100 years. So 4,200 years old. Okay. All right, let's look at some compound interest problems. All right, this says compound interest. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually, how long will it take for the account to increase to $800? Okay, it's not continuously. So because it's semi-annually, we're going to use this formula that we had several sections ago. If it said continuously, then we use A equals PE to the RT, but it's semi-annually. All right. It says $500, an account paying 8.5%, 0.085, compounded semi-annually, so that's twice a year. How long will it take for it to increase to $800? So we know everything but the time it's going to take. All right. So $800 equals $500 times 1 plus 0.085 over 2 raised to the 2t power. Okay. Now, I can take 0.085 and divide it by 2 and get a nice number. So I'm going to do that. Let's see here. 0.085 divided by 2 is 0.0425, and that's all raised to the 2t power. Then I could take 1 plus 0.0145 and get 1.0425, all to the 2t power. All right. Now, I need to solve for t, which is an exponent, so I need to change this into logarithmic form. But I've got this thing out in front in the way of me switching it around, so I got to get rid of that. So I'm going to divide both sides by $500, which gives me 8/5 equals 1.0425 to the 2t power. Now I can change that around, and I have log base 1.0425 of 8/5 equals 2t. All right. To make things a little simpler, my next step would be to what? Divide both sides by 2. Okay. So I'd get this, that. Okay. I want to do something a little easier to deal with, though. Wouldn't dividing by 2 be the same thing as multiplying by 1/2? And in fact, wouldn't multiplying by 1/2, let's try that again, be the same thing as multiplying by 0.5? I'm just trying to make it easier to put into the calculator. So I've got t equals 0.5 log base 1.0425 of 8/5. All that to get a 0.5 instead of dividing the whole mess by 2. But I need to use the change of base. So t equals 0.5 log of 8/5 over log of 1.0425. Let's put that into the calculator. Let's see what we get. 0.5 times the log of parentheses 8 divided by 5, close it up, divided by the log of 1.0425, close it up, push equals, and I get about 5.6 years. It comes out to 5.6461, et cetera, et cetera, et cetera, but they rounded to the nearest tenth of a year. Okay. Let's see here. We've got some time. Let's do another one. Another compound interest problem. If $1,300 is deposited in a savings account paying 9% interest compounded quarterly. So again, we're going to use this formula. And we've got $1,300 paying 9%, compounded 4 times a year quarterly. And then how long will it take for the amount to increase to $2,100? Okay. This is very much like the one we just did. So we've got $2,100 equals $1,300 times 1 plus 0.09 divided by 4, all raised to the, let's see, 4t power. Okay, so $2,100 equals $1,300 raised to the 1 plus, let's see, if I take 0.09 divided by 4, I get 0.0225, all to the 4t power. I can continue to simplify that further. 1 plus 0.0225 equals 1.0225, all to the 4t power. But again, I've got to get rid of that 1,300 because it's in the way. So we'll divide both sides by the $1,300. On the left side, I get 21 over 13. On the right side, I get 1.0225 to the 4t power. We're trying to solve for t, which is an exponent. We'll change this to a logarithmic equation. Log base 1.0225 of 21/13 equals 4t. I could divide both sides by 4, which is the same thing as multiplying both sides by 1/4, which is the same thing as multiplying both sides by 0.25. And again, why am I doing that? Just makes it easier to punch into the calculator. So now I get t equals 0.25. I'm going to go ahead and use change of base, log of 21/13 over the log of 1.0225. Okay, so I went from there to here using the change of base formula. So 0.25 log of 21 divided by 13, close that up, divided by log of 1.0225, close that up. And I get 5.38831, et cetera, et cetera. So rounding to the nearest tenth, the 8 would round up, so we get about 5.4 years. Okay, so our new formula, A equals A sub 0, 2 to the negative t over h power, the half-life formula. From the past, we've had this one. We've had this one. And we've had that one. Anyway, that concludes today. So again, you've got some problems from 11.6, 11.7, the chapter review, Tomorrow we'll review for a test on Friday. Have a great rest of the day.